This is Rahul and Dunyan. Today we're gonna present Dan Kamenetsky fast DNS poisoning attack. Before that, let's introduce the agenda of today. It will basically start with the background and then how the attack works and how got discovered and its disclosure and what danger did the attack pose and some implementation details and the challenges and demo for that. And then we'll end up with lessons from the attack and security implications and defense against the attack and then conclusion. So to start, DNS basically the internet phone book translating human readable domain into IP addresses to enable user to access website without needing to remember numeric IP addresses. So to improve efficiency, DNS resolvers cache the result of queries for a certain period. This means that if the same domain is requested again, the resolver can provide the answer from its cache. So while DNS caching improves performance by reducing lookup time, it also introduces a security risk. So basically, if an attacker manages to inject false DNS record into the cache, user can be redirected to malicious sites. And this attack is known as basically DNS cache poisoning. So DNS cache poisoning is a broad category of attacks. It comes with different variants such as birthday attack, and man in the middle, and Roach DNS server, and Kamenetsky attack. In this presentation, we are going to focus on Kamenetsky attack. So what is Kamenetsky attack? The attack was basically discovered by Dan Kamenetsky in 2008. It exploited a flaw related to a lack of entropy in DNS transaction IDs. How did he discover that? Basically, while analyzing DNS behavior, Kamenetsky noticed that DNS resolver would accept records for unrelated subdomains under the same domain. So basically, how this attack was disclosed, basically in July 2008, Kamenetsky privately informed major DNS vendor before making the attack public, and a coordinated effort was made to develop and deploy patches before the full disclosure. And in July 8th, a patch was released simultaneously by major DNS vendor to reduce the effectiveness of this attack. And in July, Kamenetsky finally revealed the full attack details. And then by that time, major DNS provider had already applied fixes limiting the attack impact. So basically, there are some major security risks such as widespread of domain hijacking and phishing, credential theft, malware distribution, and we have like a negative massive impact on the internet infrastructure, because almost all DNS resolver were vulnerable, making this a global threat. And now Rahul will start talking about the implementation steps.
Alright, now talking about the implementation. So the setup includes an Ubuntu 20.04 VM running 4 Docker containers, one for the attacker, one is the attacker name server, one is the user, which is the victim, and a local DNS server. And to execute the attack, we use a Go program to send spoofing packets, which are sent at a blazingly fast speed. So I'll just briefly walk through how the attack works. So what happens is that the attacker sends a DNS query for a non-existing subdomain of the target domain, say example.com. If the resolver has no cached answer, it will forward the request to the authoritative name server of example.com. Before the real name server responds, the attacker will send multiple forged DNS responses pretending to be from example.com's authoritative server, while each fake response will contain a guessed transaction ID and a malicious IP address. And this malicious IP address is basically the attacker's DNS server. Since DNS uses 16-bit transaction IDs, the attacker guesses transaction IDs in parallel to increase the success rate. And many resolvers at that time used predictable transaction IDs, making it easier to guess the correct one. So if one of the attacker's fake response matches the correct transaction ID, the resolver will accept the fake DNS record and it will cache it. And all future queries for say example.com will now resolve to the attacker's malicious IP. So overall, users trying to visit example.com will be redirected to like a fake site controlled by the attacker. And the attacker can launch phishing attacks, credential theft, and stuff like that. So now we're going to jump into the demo. So here you'll see that I've started up all the containers. We're running the attacker name server and the local DNS server. And now we're going to try to SSH into the local DNS server container and also the attacker container. So once we're inside both the containers, I've already copied in the binary of the attack. So I had already, so this is basically like the code for the binary. I had already compiled this and copied it to a shared directory with the VM. So I'm going to skip the code walkthrough for the essence of time. So if you'll see that I've already configured a shared folder with the VM, and the attack binary is already copied so that we can directly execute the attack. And the attack binary is also copied into a shared volume between the container and the VM so that we can directly run the attack. So first of all, I'll try to do a dig on example.com so that we can see how like a non-malicious DNS lookup works. So if you'll see, the root name server is the actual root name server for example.com. This is the Wireshark capture. And so before starting, I'm just going to flush the DNS cache so that we can start afresh. And now before we start our attack, we also need to know what are the actual name servers for example.com. So I'm going to run dig again to get the actual name servers. So if you'll see, these are the actual name servers: 199.43, 135.53 and 133.53. So once we have that, let's start the attack now. I've just copied the command here since the command is pretty long. So I've just copied the command here. I am specifying the target address here, which is basically the local DNS server. In the spoofed addresses, I'm going to specify the actual name servers because we want to spoof those name servers. And the attacker name server is basically the attacker name server. And once we are ready, we're going to run the attack. So before running, I've just flushed the DNS cache to be double sure. And as soon as we launch the attack, we'll request like a subdomain, and we'll again go back to our local DNS server and see if the cache is now poisoned. So as you can see, as soon as I dump the DNS cache, we can see that the cache has been poisoned. And now we can verify this by running a dig again for our the domain which we want to request. So let's try to request the domain again. So I'm just restarting the packet capture before requesting the domain. And now I'm going to do a dig again on www.example.com. So I just did a dig, and as you can see, the name server, the packet capture tells us that the name server for www.example.com was poisoned, and now it contains the ns.attacker32.com, which is basically the malicious name server. So yep. Yes, I'm just expanding the DNS packet to make sure. Yes, that's it for the demo. I'm gonna hand it over back to Donia so that we can start before handing it back to Donia, I was just like to talk about the challenges faced. Since root name servers keep rotating and changing, the same attack script which we might have tried yesterday might not work today, and we had to use raw sockets instead of the library so that packets are bombarded blazingly fast. And although the attack probability is high, this is like one of the most common challenge we faced. It's not 100% success, and we had to try a bunch of times before it succeeded. So now let's talk about lessons from the Kaminsky attack.
Now we can have like some key takeaways, such as fundamental flaws exist in the protocol because DNS was never designed with security in mind, and even small weaknesses can lead to devastating attack, and security patches should be coordinated before public disclosure to prevent mass exploitation. So the long-term security implication, we have like different ones, such as push for DNS-sec adoption. We need to have like better entropy in DNS queries, and we need to basically increase the awareness of any DNS vulnerabilities. Okay. So coming for the counter measurement, there are some defenses against the Kaminsky attack, such as source port randomization and DNS-sec, and query rate limiting, and lastly the bit encoding, which is basically the one mentioned in the paper provided. So the bit encoding is basically, it is introduced inside the paper, and the paper introduces a novel approach to mitigate cache poisoning attack by this method. How it works? So basically, when a resolver sends a DNS query, it randomly capitalizes the letter in the domain name. So upon receiving a response, the resolver checks if the capitalization and the response matches the query it sent. Why this is important? Because it increases the entropy and it is backward compatible. That is why, as this technique does not require it changes DNS protocol. So is this attack is still a threat? Kempinski attack has been mitigated, but similar attacks are still possible, such as man-in-the-middle rogue DNS server and new site challenges attack on DNS resolvers. So for future defenses, basically we can prevent similar attack. We need to ask ourselves, can a faster alternative DNSSEC can be developed for wider adoption, or can we introduce machine learning model to train these attacks, and can we like optimize DOH or DOT for further like optimization? That's it for the presentation. So in conclusion, Kaminsky attack is important in DNS security as it demonstrates how weaknesses in protocol randomness can lead to massive DNS cache poisoning, and keylessing attackers are always looking for small weaknesses, and we need security changes and other counter measurement. And these are like the references. Thank you.
Thank you.